Hello and welcome to the last class on ionic bond. Last time we discussed about how ionic bond is formed, the factors which affect the ionic bond formation, that is low ionization enthalpy of the metals, which is satisfied by group 1 and group 2 metals largely. Group 1 is better than group 2, and high electron affinity of the nonmetals, which the group 17 and 16, they satisfy. 17 is better than 16. And most importantly, the lattice enthalpy, which is defined as, I remind you, that the amount of energy released when 1 mole of ionic solid is prepared, is formed from 1 mole of the gaseous positive ion and 1 mole of gaseous negative ion, if you are talking about a univalent type of ionic compound. But the definition changes. If you are talking about calcium chloride, you need 1 mole of calcium gaseous ion with 2 moles of gaseous chloride ion to produce 1 mole of solid calcium chloride crystal. So, and you can also define lattice enthalpy in opposite way, the amount of energy that has to be supplied or absorbed by 1 mole of an ionic solid to disintegrate into their corresponding gaseous ions. So here, while the solid is formed, ionic solid is formed, lattice enthalpy is negative. It is exothermic. It is evolved. But when a lattice is broken down, lattice enthalpy is positive. So all these things you know, and you will be knowing more and more. Today we shall see how lattice enthalpy will be complicated. The net value of lattice enthalpy that is evolved is complicated by polarization effect, which will be discussed with the help of Fajan's rule, how the ultimate strength of the ionic bond is not only governed by the ionic character of the ionic bond. It may have very high ionic character or low ionic character, but when I say ionic character, I mean the dipole moment, the electric dipole moment. So that is not a determining factor for the physical properties like melting point, boiling point. When you melt an ionic solid, the ions get separated. The ions get separated, you have to rupture, break the ionic bond to separate the ions. That is not the case with covalent compounds. When you, most of the covalent compounds are gases or low melting liquids or low melting solids. But when you melt any covalent substance like solid iodine, even ice, solid ice, any covalent compound in the solid form, if you melt it, you're not at all breaking covalent bonds. You are simply weakening the intermolecular forces, may it be a stronger kind like hydrogen bonding or van der Waals forces, which are much weaker than the real chemical bond. The chemical bond, which are much stronger than the intermolecular forces, the real chemical bonds we have categorized comes into three types. One is ionic, the covalent, and metallic bond. Although a metallic bond doesn't have any real combination between two elements or two atoms, but still we can include under chemical bond. Maybe it is a kind of ionic bond, similar to ionic bond, but yes, they are strong. But the intermolecular forces are much weaker than them. We will talk about them in details. But what today we shall do is to see that the factors affecting lattice enthalpy. That I think I did discuss about that. One is, that is governed by the Coulomb's law. Force is equal to constant q dash or q by r square. So when there are two ions, and they are in a compact crystalline solid, the distance between them square and the charge, magnitude of the charge product, and K is the constant, which in SI includes the permittivity of the medium, the dielectric constant, the exact uh, permittivity of the medium. So it depends on the two charges. When I say charges, I mean magnitudes. Distance between ions, I mean adjacent positive and negative ions. That is the interionic separation. And these are the two. So lattice enthalpy is directly proportional to QQ and inversely proportional to R square. That is why if you compare lithium chloride, sodium chloride, potassium chloride, rubidium chloride, cesium chloride. Let us forget about francium. What you will find that since chloride is same, the ionic, all are ionic. We forget to give the charges. Since the magnitude of charge is same, only the distance factor will matter. Lithium plus is the smallest in size and cesium plus is the largest in size. So the R square factor goes on increasing. So the lattice enthalpy, the force of attraction between the ions gets reduced and the lattice energy decreases. So this should be the expected uh, order of lattice enthalpy. But the situation is complicated because we shall see that lithium chloride has appreciable, not predominantly, appreciable covalent character. What we call the polarization effect is appreciable. Then that reduces the lattice enthalpy. Lattice enthalpy is based on these two factors, the magnitude of charge and separation between them. And if the magnitude of charge is destroyed because of some covalent character, some overlapping of, orbitals of lithium and chlorine, then in that case, the lattice enthalpy gets reduced. So if this is the order, in fact, if you look to the electronegativity difference, the ionic character increases. The dipole moment order is cesium chloride is most ionic. Most ionic means ionic character is more. Cesium, because down the group electronegativity decreases. So chlorine remaining same, so the electronegativity difference becomes more and more, and hence the ionic character becomes more and more. and the dipole moment of the crystal is more and more. But the physical property like melting point, boiling point, they are not governed by the ionic character. They are governed by the lattice enthalpy, the net lattice enthalpy. How much energy will be required to break down the lattice from the liquid, from the solid state to the liquid state. And but the lattice enthalpy goes on this lattice enthalpy, which takes into account the magnitude of charge. Maybe the charge will be reduced by polarization effect and the separation between them. As you know, the R square factor is in the denominator and charge factor is in the numerator. You know that. Now, clearly, if you forget about lithium chloride and if the ionic compounds have predominantly ionic character, more than 80% ionic character, then lattice enthalpy is the governing factor to determine their physical properties. The polarization effects are negligible, maybe 10%, 5% covalent character that is present in sodium chloride, potassium chloride, as we shall see how they also change, but their presence is very, very small, maybe within 10%. In that case, the lattice enthalpy dominates over the polarization effect. They oppose each other. As a result, the physical properties are governed, well predicted by lattice enthalpy. So, if this is the case, this is the lattice enthalpy order. So, the melting point order is also same. Sodium chloride is about 800 something and cesium chloride is about 600 something, and there is a gradual decrease. I shall show you the exact values of their melting points. But interestingly, lithium chloride has the lowest melting point. Why? It is even lower than cesium chloride. It is because appreciable covalent character. Why? I'll tell you. Because of the small size of lithium plus, the polarizing power is more, and we shall discuss that. Because of that, the net lattice enthalpy is much lowered. Because when you melt lithium chloride, some of the lithium chloride they will be segregated into Li plus Cl minus, but some many will try to remain together as LICL. They will be moving as LICL as a single entity, such as a covalent, just like a covalent molecule. The covalent bond is not broken. In the same way, they will be sticking to each other and moving as LICL, and they will be just being detached from the other LICL having covalent character. Therefore, more is the covalent character, less is the melting point. So we have to remember two things. More the covalent character, less is the melting point. And more the, I will not say ionic character, more the lattice enthalpy, more is the melting point. So, which effect will dominate, that will be decided here. In alkali metal halides, the lattice enthalpy factor dominates. Therefore, although as we shall see, the covalent character decreases. The covalent character decreases from LiCl to CSCl. I'll tell you why in Fajan's rule. So, more the covalent character, less is the melting point. So here, cesium chloride has the minimum, lithium chloride has the maximum covalent character. So this is removed from this order. But look to these four. More is the sodium chloride relatively has more covalent character than others, but its melting point is highest, not is not having the less melting point. So these which are predominantly ionic is governed by only lattice enthalpy. The polarization effect is negligible and that will not be used to determine the melting point trend. But lithium chloride has an appreciable, not though predominant, appreciable covalent character. So that makes the net lattice enthalpy lessened, lowered, decreased, so that its melting point comes even lower than cesium chloride. In other cases, we shall see looking like ionic compounds, but because their covalent character is appreciable, the covalent nature will decide the melting point trend. One example I am giving you, say beryllium chloride, magnesium chloride, calcium chloride, strontium chloride, and barium chloride. They are these, at least these are ionic. Beryllium chloride is predominantly covalent. You shall see that. Predominantly covalent. So you might think that the analogy for sodium chloride, potassium chloride, rubidium chloride, we will extend to here. No. Because of the large charge plus 2 of each group 2 metal ion, they have appreciable covalent character compared to group 1 halides. Therefore, here the polarization effect will decide the melting point. You'll be surprised to find that accepting beryllium chloride, whose position I'll tell you, among these, the melting point goes on increasing, not decreasing like sodium chloride, potassium chloride. No. Here, the dominant factor is covalent character. More the covalent character, less is the melting point. Magnesium chloride has more covalent character, less melting point. Barium chloride has less covalent character, hence more melting point. Here I can say more ionic character, but ionic character means its polarity, dipole moment, electronegativity difference. So that will be a complicated thing. But yes, more the ionic character, more is the melting point, I can say, in this particular case when covalent nature becomes appreciable. Now, beryllium chloride is so covalent that if I show you the exact values here, no, no. That is okay. No change in the position. No change in the position. So beryllium chloride has the least melting point because it is predominantly, not appreciably, predominantly covalent. Lithium chloride was appreciably covalent, but beryllium chloride is predominantly covalent, having some ionic character, or the other way. Because we see Be2 plus has a very small size, smaller than lithium plus, smaller than Li plus, and the magnitude of charge is 2 times more. So that makes it predominantly covalent. Beryllium chloride is soluble in organic solvent like acetone, which lithium chloride have some partial solubility in acetone. Sodium chloride and all other compounds have least solubility in organic solvents. So the test that some ionic compound, I mean, looking like ionic compound is more soluble in organic solvent, will testify that that compound has predominantly covalent character. Covalent substances are soluble in organic solvents like chloroform, like carbon tetrachloride, like acetone. These are organic solvents having lower dielectric constant. Water is having high dielectric constant. The bulk polarity, as we shall study more and more, you will find there is called a term called bulk polarity. And molecular polarity. Molecular polarity may be very high. Acetone as a molecule, the dipole moment is 2.75 dBi. We shall do the calculations later. But collectively, acetone as a solvent, as a liquid, has a dielectric constant which is about 20 or maybe 25 as compared to water, which is 80. 4 times greater, bulk polarity, dielectric constant or the permittivity of the medium, that gives you the bulk polarity as in the condensed state, not in the gaseous state where the individual molecules and atoms, they exist. An individual molecule, the polarity, and collective polarity is something quite different. When we say acetone is a weakly polar solvent, you may ask later, sir, the dipole moment of acetone is 2.75 dBi, while that of water is only 1.8 dBi, 1.86 dBi. How come you are saying that acetone is a weakly polar solvent? It is because when you use as a solvent, you are looking for the collective polarity in the bulk. That is known from the dipole-dipole attraction type. Water has a strong hydrogen bonding interaction and its dielectric constant is high. And acetone has a poor dipole-dipole attraction, so it's less. So this melting point is here in this case inversely proportional to the covalent character. More the covalent character, less is the melting point. But if you talk of oxides, say since oxide is oxygen is more electronegative, 3.5, chlorine is 3. So the ionic character is more in oxides than chlorides. So if you look to this, now you will find a surprising thing. Although the polarization effect, now here the polarization effect doesn't lead. Here you will find the control will be by lattice enthalpy, oxide. They are more ionic, predominantly ionic. So if you look to the melting point of these two, magnesium oxide, so it will be in this order. But because they're predominantly ionic, but beryllium oxide having some appreciable, I don't say like chloride is a big size anion having good polarizability. So beryllium chloride was declared to be completely, I mean predominantly covalent, but I don't declare beryllium oxide as predominantly covalent. It is having appreciable covalent character because of beryllium 2 plus, but it is predominantly ionic because of appreciable covalent character. its position comes here. It is much less, not like lithium chloride, which is lower than cesium chloride, but because in oxide is it is oxide, so its melting point is coming here because of the covalent character. Appreciable covalent character. See, I'll show you the exact data that I have done here. See, lattice enthalpy now governs here. These are predominantly ionic compounds. If they're predominantly more than 70-80% ionic, maybe 70% ionic, more than that, even if there are some covalent character, they will not affect the magnitude of charge, not much, so that lattice enthalpy q dash by r square will be the governing factor for predicting the physical properties. But beryllium oxide will be having an unusually low melting point. Uh, you know, if you do not consider its covalent nature, find only say that it is ionic, then it should come first. It should have come first before magnesium oxide. But it is because it is having predominant, appreciable covalent nature, it is coming way down. 3125, this is in Kelvin, and it goes on decreasing. So, before going further, let us try to understand what is the polarization effect, what is the Fajan's rule. The relative covalent character or nature in ionic compounds can be predicted by using Fajan's rule. Now, this rule talks about two parameters. One is the polarizing power of the cation, of the metal ion, or any of the cation, positive ion, which I'll write PP, polarizing power. That term is only used for cation. That PP is directly proportional to, I'm talking of a single ion. So Q, charge, and inversely proportional to the size. That is charge density. Q by D. Q by size, supposing radius. Ionic radius, I am not talking of the cationic radius. Charge by more the charge, less the size, the charge density of the cation will be high. So that if the charge density is high, having +1 or +2 or +3 is high, then it can polarize. Uh, it can polarize the negative ion. It has got a ability to attract the electron density of the anion, so that there will be some covalent character. Some of the electron density will come to the sharing mode with the cation, so that some covalent nature will develop. So more the polarizing power, more is the covalent character. And the other one is the polarizability of the anion. Polariza. This is one word. I just say PA to distinguish between polarizing power and polarizability of the anion. If the anion is polarizable, is prone to deformation, is prone to distortion. Supposing cation is the teacher and anion is the taught, like you, and cation is teacher, maybe like me. If cation is having a power to attract the student, then it is the power of the cation, that is the polarizing power. Less the size, more the charge density, so it will have a greater power to attract the electron cloud of the anion. On the other hand, the student, if student will be Gadha Singh, will be small in size and large charge because of repulsion fact. In that case, large in size, in that case, what will happen? The electron clouds are farther away from their respective nucleus, so they have greater polarizability, greater chance of being deformed and come to the sharing mode to some extent with the cation. So if the student is very interested, passionate to study, then चार लग जाएगा. A teacher having high polarizing power and a taught negative ion having high polarizability. If both are good, then सोने पे सुहागा, then they will have appreciable covalent character. So much so, sometimes it will be more than 50%. We declare the molecule as a covalent molecule. So that, that polarizability is depends on same, directly proportional to size and also directly proportional to charge. Because more is the electron repulsion, then more its chance to go away from the nucleus and overlap. So both are directly proportional. So in this, I will give you examples only to tell the relative covalent nature. Don't talk about the physical properties. If you compare between LiCl, uh, you know, sodium chloride, potassium chloride, rubidium chloride, cesium chloride, what will be the covalent nature? Co- Covalent character, tell me. Yes, Bisma? Only covalent nature. Which will have highest covalent character, which have lowest covalent character. I'm talking here the anion is same. Only the cation, we are now only looking for the polarizing power of the cation. On that basis, we will say which has the highest covalent character and which has the lowest. Tell me.
Sir, CaCl টা highest.
Huh?
Cesium chloride টা highest.
Covalent character. Are you kidding me?
Sorry. Polarization PA টা highest নয়. LiCl.
I am not asking anything about lattice enthalpy. I am not asking about the uh, ionic character or the dipole moment. I am simply asking about their relative covalent character. Maybe 5%, maybe 2%, maybe 1%. So, whose covalent character is maximum?
Sir, LiCl.
Yes, because Li plus is a cation and the polarizing power is directly proportional to sorry, inversely proportional to size. The least size is that of lithium plus, and hence polarizing power is maximum. So you can write down before that somewhere, more the PP and PA, more is the covalent character. More the PP and PA, if one of them is more, then covalent character is more. If both are more, then covalent character is still more. More the PP means of the cation, Pa means of the anion, more is the covalent character. So if you only consider the covalent nature, maybe it is maybe appreciable 30%, it may be less than 10%, maybe it is 10, it is 7, it is here we are not going to calculate. Fajan's rule doesn't give any formula to calculate what is the covalent nature. Instead, we will be getting the formula to find out the ionic character, as well as the lattice enthalpy by using the Born-Haber cycle, by using the other data. All other data you can find the lattice enthalpy. Well, lattice enthalpy is being complicated, is being lowered because of the polarization effect. That can be experimentally found out by using the Born-Haber cycle. Do the reaction in one go in a, you know, uh, in a device which will record the temperature change, calorimeter. Find the enthalpy change in one step reaction and then perform multi-step reactions. Take the metal in solid state, vaporize it, sublimation energy, then ionization enthalpy, then keep it there, then take the non-metal ion, non-metal, if it is a diatomic molecule, chop it off using half bond dissociation energy, then feed electrons to produce the anions, so that you get energy, that is electron affinity is evolved, that is the negative term, and then combine the gaseous positive ion, gaseous negative ion, and see how the the ionic solid is formed. That the lattice enthalpy, that you cannot measure, but all other terms you can measure, so that you can find during the formation of lithium chloride what is the lattice enthalpy. You will find it will be lowered, much lowered, because of the polarization effect. When solid is formed, then immediately polarization effect comes in, appreciable covalent character sets in, so that its ultimate lattice enthalpy will be lowered, which will say decide, will be used to predict its melting point being the lowest among the alkali metal fluorides. So you will write like this, because Li plus, Na plus, K plus, and so on. Now, if I say keeping sodium fixed, starts from fluoride, chloride, bromide, iodide, what will be the order of their covalent character? I'm only considering the relative covalent character. What sign I'll give is तुम्हें स्वयंजीत, are you in deep sleep mode?
No, sir.
Then tell me what is the relative covalent character. Is it increasing trend or decreasing trend? Smart.
पर एमने एमने फ्रो ची हाईएस्ट एनआई रा होती लोएस्ट.
Are you kidding me? Always you are telling the opposite answer. Wrong answer. Here we are measuring the anion's polarizability. The size increases down the group, whether it is atoms or on anions. So as the size increases, the polarizability increases. I have told you that more is the size, more it is prone for distortion or polarization to form, to have more covalent character. So when you are comparing the anions, size is directly proportional to the covalent character. So as size increases, the polarizability increases and hence the covalent nature increases. So what sign I'll give? Less than or greater than greater than? Please, Swamjit?
Sir, greater than. Sir, মানে sodium fluoride is less than sodium chloride. Sir, is less than sodium bromide. Sir, ଏଭଳିଆ.
Greater than କହୁଛ କଣ ସାଇନ୍ ଦେବି?
Sir, less than.
ତାହେଲେ greater than କେମିତି କହୁଛ? ଯଦି ବଢି ବଢିକି ଯାଉଛି, because I am not using any ଓଡ଼ିଆ term, you are now scared. ବଢି ବଢିକି ଯେତେବେଳେ ଯାଉଛି ସେତେବେଳେ ମୁଁ କଣ ଦେବି? ସାଇଜ୍ ଅଫ୍ ଦି ଆନାୟନ ବଢିଲେ polarizability ବଢେ, polarizability ବଢିଲେ percentage of covalent character ବଢେ. ତେଣୁ sodium iodide has, I am not saying they are covalent substances, they are predominantly ionic. They are predominantly ionic. And therefore, when you talk about their lattice enthalpy, the highest is sodium fluoride. That doesn't consider anything. It considers only Q dash by R square. But because it is predominantly ionic, so the melting point trend will be opposite. Sodium fluoride is the highest, then sodium chloride, then sodium bromide, then sodium iodide. But sodium iodide is more soluble in acetone than sodium bromide, sodium chloride, sodium fluoride. Since sodium iodide has comparatively more covalent nature, covalent compounds, as we shall discuss, are more soluble in organic solvents, less polar solvent. So that doesn't mean that its melting point is the highest, because it's of course this also matches with our slogan that more the covalent character, less the melting point. So sodium iodide has more covalent character, less melting point. I have not shown you the melting point order. This is the covalent nature order, nothing other than that, because I am blending different concepts together. That has been my passion these days. Therefore, I am choosing one or two students to satiate my passion. I can say whatever I want, and you can ask me whatever you want. This is merely to judge the relative covalent nature, not to judge the relative, lattice enthalpy order or melting point order or the ionic nature. The ionic nature will be governed by electronegativity difference. In case of alkali metal halides, we saw that the ionic nature increases down the group. Cesium and chlorine has the highest electronegativity difference, so the dipole moment is maximum. But what happened to its melting point? Is the least. But lithium chloride having the minimum ionic character, appreciable covalent character, its lattice enthalpy is not the highest because of appreciable covalent character. Its net lattice enthalpy is even lower than cesium chloride, so its melting point comes, below cesium chloride. But here, supposing I will consider stannous chloride and stannic chloride, which will be having more covalent character. Tell me, which will have more covalent character?
Sir, essential 4.
Precisely, this is +2, this is +4. So more is the charge of the cation, more is the polarizing power of the cation, and more is the polarizing power of the cation, more is its covalent nature. So essential 2 is less covalent than essential 4. That will be reflected here. The polarization effect governs the melting point. So melting point of SnCl2 is greater than SnCl4. Is more covalent, less melting point. It is a solid at room temperature. Therefore, its melting point is high. This is a liquid. Can you imagine? At room temperature. Having 4 chlorine atoms, so bulky, but it is in the room temperature, it is a liquid. Having lower boiling melting point. Melting point is sub room temperature. Sub is lower than room temperature. You have to cool down to get it solid state. But stannous chloride is itself a solid, and you need to heat it to melt it. So similarly, you can have ferrous chloride and ferric chloride, which is more ionic, which is more covalent. Hmm? So what is the covalent nature? Which is greater? Hmm?
Sir, FeCl3 is greater.
Yes. Eta +3, eta +2. More is the charge, more is the polarizing power. So देखिए melting point range ferrous chloride will having more melting point than ferric chloride because ferric chloride has larger covalent character. Supposing we will consider lithium fluoride, lithium plus has appreciable polarizing power. So lithium compounds are having appreciable covalent character. But fluorides of every metal are predominantly ionic. Even it is beryllium. Beryllium fluoride is ionic. And all other beryllium compounds. Beryllium oxide is also predominantly ionic. All other beryllium compounds are predominantly covalent. Because of high polarizing power of Be2 plus. Ultimately, Be2 plus rauni. Ionic rauni. The polarization effect will make it predominantly covalent in sharing mode. Supposing you will compare between lithium fluoride, lithium chloride, lithium bromide, and lithium iodide. So what will be lithium ion remaining same? Lithium itself has high polarizing power, has appreciable covalent character in all compounds other than fluoride. Other than fluoride, which is predominant, of course, lithium chloride is predominantly ionic, but having appreciable covalent character. But what will happen in this? In this covalent nature कार सबुठु अधिका हबो
Sir,
Sir, lithium iodide.
lithium iodide.
yes now lithium iodide 50% covalent and 50% ionic it's so lithium plus is having appreciable polarizing power. Iodide ion is too hefty, have a high polarizability. So I becomes 50%. I'm showing you some more examples to here. See, 50% covalent character. You see, I've given only covalent nature. Beryllium chloride is most, because Be2 plus, this is Mg2 plus size. Although 2 plus remains same, but size increases means size is in the denominator, the polarizing power decreases, and hence the covalent nature uh, decreases. And here, as I have told you, the guiding aspect for melting point is the polarization effect. Beryllium chloride is most covalent and hence least melting point. And as the covalent nature goes on decreasing, the melting point goes on increasing. Barium chloride, last one, has the highest melting point I had shown you. This I have written melting point here. So don't confuse in some batch. And the third point I forgot. I forgot the third point about the cation. Cation, I told only 2 points. And another point is a pseudo noble gas configuration. That is 18 electrons. NS2, NP6, ND10. So 3s2, 3p6, 3d10. If certain ion, positive ion, has 18 electrons, pseudo-noble gas configuration has high polarizing power because the D has poor screening effect. The example that we will take up is between silver chloride and sodium chloride. Let us make it ionic, but actually silver chloride will be found to be predominantly covalent because silver plus will be 5s0. This is 4s2, 4p6, 5s1, 4d10. So 4d10. 5s1 is gone. So this is 18 electrons, pseudo-noble gas configuration, and therefore its polarizing power is more because of the poor screening effect of d electrons. That is why the covalent character of silver chloride is much more. It is predominantly covalent, while sodium chloride is predominantly ionic. And therefore the melting point of sodium chloride is more, silver chloride is less. And it is soluble in organic solvents more than sodium chloride. So this I have shown here as an example. See, more the covalent character, more is the solubility in organic solvents like acetone, benzene, ether. If you compare in a period lithium chloride, beryllium chloride, boron chloride, you will find the covalent nature will increase. So much so that beryllium chloride becomes predominantly covalent. Forget about boron chloride is covalent. More covalent than beryllium chloride because B has plus 3 charge. So you write down everything. This is polarization effect, Fajan's rule, and I have explained how the power of the cation can able to attract the large electron cloud. If at all it is large and more in charge, then it can be deformed and have some covalent sharing character. This I already discussed everything. Factors affecting lattice enthalpy I have told you, and how lattice enthalpy is being complicated by polarization effect. I have given you examples, these examples. And also lattice enthalpy, you see the melting point difference between magnesium oxide and sodium chloride. Both are ionic, but there is some polarization effect in magnesium oxide, but it is predominantly ionic. But since the charge factor is 4 times more, 2, 2, this is 1, 1. Therefore, the net lattice enthalpy is much greater. So much so, not exactly 4 times, because there is some polarization effect, but more than 3 times, as you find the melting point also is about 3 times more than that of sodium chloride. And sodium chloride has a slightly greater melting point than calcium chloride. Although its calcium chloride should have been more melting because it has got more charge, +2, this is +1. But it is again complicated to some extent by the polarizing power of calcium 2 plus having some little more covalent character. That makes the net lattice enthalpy little less than that of sodium chloride. So these things, the actual lattice enthalpy and hence bond energy, because lattice enthalpy governs the bond energy, is complicated by polarization effect. We have already seen Born-Haber cycle, how to determine lattice enthalpy. And this problem you will be doing. I have given a problem, I have given all the data, you will solve this problem. I have solved, but you solve of your own. Next time, we shall be talking of this Born-Landé equation is not required. This is another way to find uh, the bond energy of ionic bond, taking permittivity of the medium and interanic distance, permittivity, and this is not required. Now, then next time we'll talk about the properties of ionic compounds. That is a small part. We cannot finish today. Yes. Then we shall pass on to the. We will be finishing that on 22nd. Today is 20th. 22nd, that is on Friday. But we'll be having maybe 1 hour class, 5 to 6. Yeah, because I will be going for a outside trip for 3 days for a conference. And so I'll be back on 25th. 25th is your day, Monday. So we won't have class on 25th. We'll be having class on 27th, which will be Ganesh Puja. But many houses, many homes, they don't allow their children to study on Ganesh Puja. But before your parents wake up, we will finish our clandestine, so-called clandestine meeting and study. କଣ କହୁଛ?
Yes, sir.
Yes, sir.
କଣ ମୋ ଗଣେଶ ହଉଛି ପାଠଙ୍କର ସେ ଗୁରୁ। ସେଦିନ ପାଠ କାଗଜ କଲମ କଲମ ଫଲମ ରଖିକିରି ପଢିବାନି. This is a superstition that is being followed long from time immemorial. So let us break it. ଗଣେଶକୁ ଆମେ ଭଲ ପାଉ, ଦେଖିବାକୁ ବଢିଆ, ପେଟଟି ପୁରା ଏଟେ ବଡ, that is indicative of the overall petto nature in our country. In most of these oriental countries where petto comes larger when you are a child now, kid, when you grow up above 24, 25, the more age you add, the more petto you grow. Of course, I am not saying it is the case with all, but say 80% majority of the public in these areas, they have large petals. So Ganesh, why Ganesh has been made so petu? And we love to see the elephant-like face of Ganesh. We have been loving Ganesh since our childhood. The moment we see Ganesh, we are filled with devotion. Devotion is, surrender. Love, devotion, surrender, they are synonymous. And then compassion comes. Karuna automatic asila. That is the reason for which we worship or we pray or we uh, follow any faith, religious faith, to develop karuna, compassion, and work for others, not to become jealous, but to support others. If that quality doesn't come to us, then bhad mein jaye this religion, bhad mein jaye this, loving Ganesh. कुछ नहीं होता है. Lifelong life is a waste if somebody professes a religion and is, coward, fears everything, doesn't speak out what comes in his mind, even in a meeting where there is no hooligan, no mafia to put you in a gunpoint. Just for nothing, you are shy, you are not only shy but also fearful to talk. Se kon bhabibo, loke kon kahibe. And we don't intend to help others. More kon jauchi mu taku kahi help karibi. मोर मु आराम रहे. सो दिस मु मोर जो एटीट्यूड जो पर्यंत आम रही ये पूजा पत्र किसी मूल्य ही नहीं. बाय बाय.
Thank you, sir.
Thank you, sir.